interrupted trace of x, which I'll call y.
And what does that mean? Which means that each bit of the string x is deleted independently with probability p. And this is like really like the deletion channel in coding. So all the bits get squished together, and that's what you see. So you hit the button, lightning strikes like about half of the bits, and you see this string here. Okay, and then of course you don't know what x is. Your goal is to figure out what x is. So you like hit the button again, and lightning strikes a different half the bits, and you get this string, possibly of a different length. You hit the button again, you get some other string. You hit the button as many times as you want, and at some point you have to like guess what x is. So these are all your these are called traces. Okay, yeah. So does anybody remember what x was? No, right? So it's not so easy. I mean, somehow like it's some super string of all these things that's like consistent with all these traces. That's what you have to figure out. Okay. And the main question we want to know is like, how many traces do you need to recover x with high probability? Yeah.
Is n known?
Yeah. Let's say n is known. Yeah. And you can also ask, you know, what about the running time? Like, so you can ask information theoretically, how many traces do you need? And then also, can you figure out x from that these traces efficiently? We worry about that in the paper, but in this talk, I'm not really going to worry about running time, just the information theory problem. Here's one trivial upper bound. You can do it with about 2 to the n traces. Does anybody know how to do that?
Just wait for the whole thing.
Yeah, just wait around until you see a length n trace, and then you'll be like, I guess nothing was deleted, and this is the answer. Good. Remark 2, it's actually without loss of generality, basically that the x's symbols are 0 and 1. You might imagine trying to do this trace reconstruction over a larger alphabet, where like each symbol is deleted with probability of half. But you can easily reduce to that case if you can solve the problem where the alphabet is 0 and 1. So first of all, like let's say if you have an alphabet of size 4, A, C, G, and D, then just in your traces, whenever you see an A, you think 1, and when you ever see one of the other letters, you think 0. And then if you solve the trace reconstruction problem, then you've exactly learned where the A's are in the string. Okay, and then you can just do it again, treating C as 1, and then treating G as 1, and then treating T as 1. And you solve the problem 4 times, and you learn the position of all the letters. Okay, so we can restrict attention to 0, 1 strings and solve the general alphabet problem too. Okay. One more parameter here. I fixed that the probability that each bit being deleted is a half. It's not obvious, but it turns out that this parameter really doesn't matter that much. And our results are going to be the same whether this parameter is 99% or whether it's 1% up to some constants. So let's just fix it to be a half for simplicity. Okay, and this is our theorem. It's hard to tell how good it is, but that's it. You can do it, we show, using basically 2 to the n to the 1/3 many traces. And if you change that probability a half of the running time, like we know how it changes the big O, but never mind. And as I said, we show that you can do it with this many traces and also this much running time. But I'm not going to show you the running time part. I'll just show you like a non-efficient algorithm for doing it with this many traces. Okay, and what is our algorithm? It's like a very stupid algorithm called the mean trace method. So you just draw a bunch of traces, hit that button this many times. Just estimate the mean of each coordinate for each of the n up to n coordinates you see. Just estimate the fraction of time you see a 1 in that coordinate. And so now you have all these estimates. And then the non-efficient thing to do is just output the maximum likelihood x, the one that's like most likely to have generated these means. And that's it. So our algorithm like does something stupid, kind of stupid in the sense that like it only looks at like the n positions in the trace like individually, and just estimates the probability of seeing a 1 in each of them. As I mentioned, we can actually turn this into an efficient algorithm, efficient in the number of traces, but I'll skip that.
Sorry, just to clarify, after this much time you're sure about what it is, or after this much time you're arbitrarily sure about?
Yeah, with high probability, you'll have the correct value of x.
But it might be possible, and like little through the end, to be sure before.
No, because I mean, like a huge disaster could happen where like every time you hit the button, you get an empty trace, like everything is deleted. That happens with positive probability.
With high probability, you will be sure. Not Right, so the question is on the probability that you can terminate, like, let's say when you terminate, you're sure. Is the probability on your running time or the correctness of your output, right?
Oh, you want a situation where you're totally sure and you like use an expectation, like a small number of examples? I mean, probably you could just like repeat this algorithm like lots of times. This gives you x with high probability. Oh, yeah, I'm not totally sure. I mean, the only way you can be really, really sure, I think, is...
So yeah, the truth is
actually, no.
The string.
I'm not sure, actually, because it's a good point that there are some circumstances where you'll like, at some point you'll say like, man, I know for sure x is definitely this, and our algorithm is not like that. Good point. Yep.
Yeah, so how do you know which position in the traces correspond to which original position?
You don't. That's the hard part. So like if like instead of the bits being, to use the coding theory terminology, if instead of the bits being deleted, they were erased, like just replaced by question mark, then it'd be super trivial. I mean, you would just like draw a bunch of traces and like wait until you see a non-question mark in each coordinate.
Oh, I see. Like you're gonna say how it works.
Yeah, we're gonna show. I mean, one of the difficulties is like the alignment. Like, I mean, you see like, you know, n over 2-ish bits, and you don't exactly know how they align back to the original n bits.
Okay. So like the estimating the new i's are the hard ones.
No, here this is the probability that the ith coordinate of the trace is 1.
Oh, I see.
Yeah, so this is easy. I mean, this is really just like the probability that you get a 1 in the very first coordinate, and the probability you get a 2 in the very first coordinate. In some cases, y is only so long. Okay, in which case, like, you know, I guess mu n will be very small because you almost never even see a bit in the nth coordinate at all. Actually, I'm kind of like...
It's not 1.
Yeah, I'm actually cheating a little. Eventually, what we do is like treat the true bits as plus or minus 1, and then like you treat y as being a sequence of pluses, minuses, and zeros, with like the zeros being at the end, saying like, you know, nothing was there. And then it's better to like compute the mean of that. But like this will also work. So as you say, like you can also just treat it as like, well, you didn't get a 1 if you don't even have that many bits.
So in the special case where suppose I take like 2 to the n traces,
Yeah.
it's obvious that this algorithm works?
No, I don't think so. I don't think so.
Like even if like one of your samples is the actual input?
Yeah, I mean, this algorithm does not use that fact, yeah. Which is kind of weird. Yes?
So is it possible for the mu's at the end to just not be defined with high probability?
Well, let's say that, you know, like, it's literally like this in the sense that, like, if you get a trace y that is of length, you know, 0.6n, then for that draw, for every position I that exceeds 0.6n, you're like, well, yi does not equal 1, doesn't even exist. So it doesn't contribute to this mu. Yeah. Our second theorem is that our analysis of our own algorithm is tight, in the sense that, like, if you just do this, you need to the n to the 1/3 samples. Yes?
Wait, are you distinguishing traces when like there's an ending 0 versus there's no ending 0?
Pardon me?
Like if the 0 at the end is erased, do you like, is this algorithm the same? Like
Yeah, I guess so. I mean, yeah, everybody, okay, think about it this way instead. Like, what we actually eventually do is, instead of calling the bits 0 and 1, call them plus or minus 1. And then, like, think of a trace y as a sequence of plus or minus 1s, followed by, like, infinitely many if you want, or enough zeros to pad it out to length n. And then compute the expectation.
okay.
The expectation of the ith coordinate. And call that mu I.
So just to be clear, like, I mean, if you're taking only 2 to the 10 to the 1/3 samples, you're never going to see a full string. I mean, with reasonable chance, you're never going to see the full string.
Right.
So in that case, mu n is going to be like 0.
Yeah. I mean, you're pretty much going to see like n over 2 every time. So like, I think it would also not be a big deal if you just like only looked at the first n over 2 positions here. Or in fact, also, as I said, like, it doesn't really matter what p is. So like, you could, yeah, anyway.
You could always take exactly n over 2 in your trace. Like your trace could be a fixed n over, like a fixed length instead of.
Yeah, or you could like artificially make p bigger yourself by like deleting some extra bits to like simulate p equals 0.6, and then like you never. Okay, anyway.
So is is the maximum likelihood step obvious? Like, given this mu...
No, that's the whole point of the theorem. That like this many samples is enough such that the maximum likelihood x will be the true x with high probability. Okay.
So I can just follow up. So is the hard part computing the maximum or showing that through the end of the 1/3 is enough so that with high probability the maximum likelihood is right?
The latter. That's like most of the work to show that with this many traces, knowing this mean trace, your estimate of the mean trace is like good enough that the maximum likelihood x will be the true x with high probability. Then we have like the separate thing where we show, oh, you don't actually have to do the maximum likelihood. You can do an algorithm that will find it. Yes?
So for the earlier question where you want to be sure with probability 1
Yeah.
that this is the string, so you said here that you need 2 to the order n samples. For example, if you only restrict to strings, let's say 2 strings, all of these are 0 and just either the n over 2th coordinate is 1 or n over 2 plus 1th coordinate is 1. Then in order to be sure with probability 1, you need to see n over 2, roughly n over 2 zeros either before or after that.
Yeah.
You need to the order n over 2 things.
Yeah, I think you're right. And I think that answers Wes's question. So in fact, that's also a good point in the sense that like what we really show for this is that like for any 2 distinct x's that it could be, once you have this many traces, the mean trace is enough to distinguish between these 2 potential unknown strings. Okay. Okay, here's some more remarks. Pretty much the same results, except they didn't have the algorithm was proved by Nazarov and Perez at the same time. It's been studied for 15 years. Prior to our work, there's basically one prior result, and it got a 2 to the n to the 1/2 samples in time algorithm. And they proved an n to the log n lower bound on our style of result, this mean trace algorithm. Okay, so we got a mean trace based algorithm that got 2 to the n to the 1/3 and also proved the matching lower bounds. I said this one already. And our paper also has some stuff about like what if there's like insertions and substitutions when you hit the button, but basically deletions is the hardest case, so let me also just focus on that. Okay. So this is what we're going to do. Mainly focus on the upper bound. Actually, I'm not going to talk about the lower bound very much. And there's going to be like a big jump now. It's like, well, I told you what like trace reconstruction is. Now I'm going to start talking about some totally different thing. And then like, when there's like 10 minutes left, I'm going to bring it all together. Okay, so get ready. Okay, so this is what happened. This was about 2 years ago, 1 year ago. So here we are. That's me. That's in India. That's Rocco. And we're all at this conference in Germany. So that's Germany. Yeah, so I don't know, we were just like, between the talks, and we were like, hey, let's talk about some problem. We decided to talk about this problem, which we'd heard about. And we talked about it for a few sessions. And after a while, we arrived at some kind of analytic question. And we got stuck. And then we had nothing. And then like Rock and I are just eating breakfast one day. And an India came in. He's like, hey, I reduced everything, where we were stuck to just like one very simple like mathematical question. And I was like, great, what is it? And he said, okay, let P of z be a Littlewood polynomial of degree less than n. And I was like, what's a Littlewood polynomial? And Rocco knows a lot of stuff. He's like, I know this. He's like, it's a polynomial where every coefficient is either -1, 0, or +1. I was like, okay. Okay, so Ananya says, let P of z be a Littlewood polynomial of degree at most n or less than n. I always like to think about concrete examples. So in my mind, I'm like, okay, here's an example. This is a Littlewood polynomial. All the coefficients are 0, 1, or -1. And even in my head, I like plotted it. Right? So this is a polynomial. And he's like, this is the question we got to answer. He's like, if we can answer this question, man, we're going to nail the whole trace reconstruction problem. And I'm like, oh, great. So let's take a look at it. He wants to look maximum absolute value that P of z must have on this region where z differs from a half by at most a half. So like in this particular example, there's a point z where you differ from a half by at most a half, where P of z's magnitude is this big. And he kind of wants to like ask, what's the worst Littlewood polynomial for this? Among all the Littlewood polynomials, like which one has the smallest maximum here? Okay. And Rocco is, he's a smart guy. He also knows the literature very well. So he's like, actually, I know the answer to this one due to like some previous work. It's basically exponential in minus n to the 1/2. That's the answer. And then India is like, oh, you thought I was talking about the reals. I was talking about the complex numbers. And I was like, complex numbers. Nobody wants the complex numbers, right? I don't. But that's what he was talking about over the complexes. So that changes everything, right? It's revolutionized. So this is the plot of this Littlewood polynomial over the complex numbers, or the magnitude of this polynomial over the complex numbers. And so this question it's all different now. This is the complex circle, and this region that he's talking about is everything in this yellow disk, everything at distance at most a half from the real value a half. And this could actually make the answer larger, right? Because you're going over all Littlewood polynomials and trying to say that no matter what the Littlewood polynomial is, it's got to have a pretty large value somewhere on this disk. Instead of it just having a pretty large value on this like diameter of the disk, it's just anywhere in the complex disk. Great. So I think there's no more jokes in this talk. So this is our main theorem, in some sense, our main technical theorem. Suppose you have any non-zero Littlewood polynomial of degree bounded by n, then somewhere in this disk, the polynomial takes on a value that's at least exponential in minus n to the 1/3. And yes, this is going to be the same, 2 to the minus n to the 1/3 that gives the trace reconstruction result. And that's what I want to prove to you. So are we ready? Let's try to prove it. Yeah?
For general p, would that be something like z minus 1 minus p with the most p, or vice versa? Or? Oh
yeah, this 0.5 being here and here is also because the deletion probability is 0.5. And if like the deletion probability was like 0.7, then you'd be looking for like a large value of the polynomial on like this disk here centered at 0.7 and touching 1. Excellent point. Okay, so step 1. First of all, is like look for the lowest appearing power of z. And factorize your polynomial like this. So z to the power of d times something that's, well, plus or minus 1, but not 0. Okay? Let me call this q of z. Now, it's also a Littlewood polynomial. Now, the magnitude of p of z is just like the magnitude of z to the power of d times the magnitude of q of z. And there's basically no reason why d could not be like linear in n. Like it's perfectly possible for d to be, I don't know, n over 2. And then you basically have kind of the same problem, like a Littlewood polynomial of degree n over 2 times z to the n over 2. Which basically means that this point you're looking for somewhere in the disk had better be like super close to 1. Because magnitude of z to the d is tiny unless z is very close to 1. And there's no reason d couldn't be like n over 2. So you better put your magnifying glass here to look for a point. Okay, so I've zoomed in. Good, so now this is our situation. P of z is z to the d times some Littlewood polynomial q that starts with plus or minus 1. Without loss of generality, say it starts with plus 1. Actually, I'm no longer even going to need the fact that the degree is bounded by n. Q's degree is bounded by n. I'm just going to need the fact that d is at most n. Okay, so turns out the strategy next is I'm going to look for this special z where p has a large value. I'm going to look for it on this blue arc. What is this blue arc? It's part of the circle centered at 1/3 and passing through 1 minus epsilon. So basically, for some parameter epsilon to be named later, like here's a point 1 minus epsilon, and then way back here there's like the point 1/3. Draw the circle centered at 1/3 that passes through this point, And it's going to actually intersect the yellow disk at some points, and like that's the blue arc. Okay, and I'm even going to just restrict attention to trying to find a good z on this blue arc. Okay, so this point is 1 minus epsilon, but actually, I mean, these are little tiny elementary calculations. All the points on the blue arc have magnitude at least 1 minus big O of epsilon. It's not hard to calculate with a little geometry. So our main lemma, our main theorem is going to be this one actually, that when Q is a Littlewood polynomial with a constant coefficient that's not 0, there's some point on the blue arc where Q's magnitude is at least exponential in minus 1 over root epsilon. That's going to be like our new theorem goal. And I claim that once we have this thing, then we're done. Because then for this particular z hat, the magnitude of p of z hat, well, it's at least 1 minus order epsilon to the d. That's accounting for this part here. Times q at z hat, which is at least this exponential in minus 1 over root epsilon. And then you choose epsilon to balance the parameters. Okay, so this is like 1 minus epsilon is like e to the minus epsilon. This d, in the worst case, it's like n. So we have exponential in minus epsilon n and exponential in minus 1 over root epsilon. And then the best epsilon is n to the minus 2/3. Okay, so having decided on this blue arc strategy, it remains to prove this theorem here. Any questions about that? Okay. Yeah.
Why did you choose 1/3? Is that for arbitrary?
Oh yeah, 1/3 is a good question. Not very important. Basically, like any explicit constant between like 0 and 1 would have been fine. Yeah. Okay. 1/3 is going to make like one calculation that's going to appear like 1 or 2 slides like slightly easier. It's a good point though. Okay, so let's try to retain everything on the slide that we need, which is this. Okay, so Q is this Littlewood polynomial that starts with +1. It's blue arc we defined, and we want to find a point in the blue arc where Q of z has a large magnitude. And this is another little elementary fact that you just easily check. The length of this blue arc is proportional to root epsilon. It's like a circle, right? So like cosine is quadratic near its maximum, something like that. Okay, so we have this arc of length root epsilon. It's like epsilon away from the outer circle. We want to find a big value of Q on it. Okay. So this Q might look like this. And here's why I chose 1/3 to make things a little bit easier. So let's look at the magnitude of Q at 1/3, that center point, which is like back here on the real axis. And you see, I want to claim that the magnitude of Q at 1/3 is at least something. And like, since Q looks like this, like what's the least it could be? The least it could be is like 1 minus 1/3, minus 1/3 squared, minus 1/3 cubed, etc. Which geometric series adds up to a half. So this is basically almost all we're going to use about Q. Well, I guess we'll use a little bit more, but like Q's pretty big. It's at least a half at the center of this circle, at this red dot. And we want to somehow infer that it's at least not super tiny. It's like at least a tiny bit big somewhere on this blue arc. Okay. Okay, so now I zoomed out a little bit. This is not to scale, but this is our picture. Okay, so I'm going to mostly tell you how to prove this. I'm going to omit some details, but I'll mostly tell you how to prove this. Okay, this is like the only place where like complex numbers really play a role. There's this fact that I did not know prior to this project, but I learned it, about complex polynomials. It goes under the name Mahler measure. And it says the following. Whenever you have like a circle in the complex plane and a polynomial, the geometric mean of the magnitude of the polynomial's values around the circle is at least the magnitude of the polynomial at the center of the circle. That's, there's all these like facts about complex numbers that are cool, and I guess this is one of them.
Circle's important there? Like,
Yes, yeah, circle's important. But in fact, I can even tell you the proof of this. You could prove it yourself with this hint. I mean, the geometric mean of a polynomial is, well, the geometric mean is multiplicative. If you multiply two things together and like take the geometric mean around a circle, it's like the product of the geometric means. And so you can take your polynomial and factorize it. So over the complexes, you can factorize it into a product of linear factors. And therefore, like, to prove this Mahler measure thing, it just suffices to prove it when it's a linear polynomial. R of z is z minus a. And then it's just a calculation. It's like you do one calculation in integral. Okay, so we just have to accept this fact now, and hopefully you start to see like how it might be relevant because we have this polynomial q, and we just showed up here that it's pretty big on the center, and that's going to imply, I guess, by this Mahler measure thing that like the geometric mean of q's values around the red circle is at least a half. Well, that's impossible to read. Okay. So we know the geometric mean of this polynomial q around this red, well, the red plus blue circle is at least a half. We're trying to show that its value is big somewhere in the blue segment. So if we can just show that like its values on the red segment are not like extraordinarily large, then that will imply that the geometric mean over the blue segment is not extraordinarily small. And this is another thing, I won't fully prove it, but I can tell you it's not very hard. The geometric mean just around this red letter C is actually bounded by a constant. And this uses the fact that Q is a Littlewood polynomial. Because, okay, here's the hint. I have lots of time, I'm going to spell it out a little bit. I mean, Q cannot be that big if you're bounded away from the circle of radius 1. Because if you're at distance like 1 minus, sorry, if you're at distance at least delta away from this circle, the biggest this can be is 1 plus 1 minus delta plus 1 minus delta squared plus 1 minus delta cubed and so forth, which adds up to 1 over delta. So just by the virtue of the fact that Q is Littlewood, like it cannot be like enormous. If you go like a little bit inside this white circle, white dotted circle, Q's value cannot be enormous. And this red C, it's almost always quite bounded away from the white circle. So you can do an integral or a little calculation and prove this fact, that the geometric mean of Q around this red C is bounded by a constant. And that's most of the geometric mean of Q around the whole circle. So this circle has circumference is like some absolute constant. And I told you before that the length of the blue arc is proportional to root epsilon. So the geometric mean of Q around the circle is basically like the geometric mean of the red part to the power of mostly 1 minus root epsilon, times the geometric mean along the blue arc to the power of root epsilon. Like this is basically the proportional length of the blue arc. This is the proportional length of the red arc. We upper bounded this. And therefore, eventually, we can lower bound this. Does that make sense? Okay, so then we just, I guess that's it. So let's see. This is a constant. We put it to this side. We have some other absolute constant here. Then we raise both sides to the 1 over root epsilon. And we get this lower bound for even the geometric mean of Q's magnitude along the blue arc. Okay, so if the geometric mean is at least this, then there has to be at least one point where it's at least that. Okay, so that's it. That's all the complex numbers, I think. Any questions? Okay, so right. So now you might be a little annoyed and ask, what does this have to do with trace reconstruction? Like, why do we take this long digression to like complex circles and whatnot? Okay, well, I can tell you it's not too hard. Okay, so I'll remind you what trace reconstruction is. It's this. There's some fixed unknown string x. You hit the button. Each bit is deleted with some probability like a half. That gives you these traces, and you want to keep hitting the button, getting a bunch of traces, and finally guess what x is. As I promised, maybe I should have just started with this. Like, my favorite thing in the world is to switch the notation so bits are plus or minus 1 instead. So let's do that. So the traces now look like this. And yeah, this is our algorithm, the mean trace method. And as I said, what we're actually going to do is estimate the mean of each coordinate in this plus or minus 1 notation. And you can think now of like absence of a bit, like towards the end of the trace, as being a 0. And yeah, this was getting at the statement from before. So what you actually really need to show in order to prove this is exactly this. So let's take a look at this for 1 second. Suppose you knew that for every pair of strings, like imagine an adversary has even promised you, you know, that unknown string, it's either x or it's x prime, and you just have to figure out which one. Is it x or x prime? On one hand, you have to be able to solve that problem in order to solve the overall problem, but it's actually enough to show that the maximum likelihood method works if you can always solve that problem for any pair of two strings. If for any pair of two unknown strings you can always distinguish them successfully, then the maximum likelihood method is going to work. And what does that really mean? It just means that if you have two distinct strings, x and x prime, you want it to be the case that their mean traces look different. So for a given one unknown string x, it has some true mean trace that it would imply. And for another unknown string x prime, it would have some true mean trace, maybe call it mu prime vector, that it would imply. And if these two vectors are sufficiently different that an estimate will notice that, then you can, in principle, distinguish x and x prime. So really, it just boils down to showing that for every x and x prime, the associated mean trace vectors are a little bit far apart. And you know, since this is already exponentially small, we don't really care about factors of n or anything. So two vectors are far apart, basically, if and only if there's a coordinate where they're a little bit far, up to a factor of n. So this is what we need to show, or what we're going to show, and it will suffice to show that this maximum likelihood algorithm works. So we want to show that for any two strings x and x prime, there's some coordinate that's like slightly good at helping you distinguish between x and x prime, in the sense that the expected value of the jth trace bit under x and the expected value of the jth trace bit under under x prime differ by at least exponential n minus n to the 1/3. Does that make some sense? Okay. So this is what we now want to show. Now here's the funny move. This is a crazy move that we'll insert. So I claim that this is true if there's some complex number w of magnitude at most 1 such that this inequality holds. And I guess let's just look at why this implies this. So this is the sum of n things. So by the triangle inequality, if this sum's magnitude is at least n times this target, then one of the sum n's magnitudes has to be at least e to the minus n to the 1/3. And if one of the sum n's has magnitude at least, our target, e to the minus n to the 1/3, well, I mean, the magnitude of the sum n is like the magnitude of this difference times the magnitude of w to the j. And, well, w is a number whose magnitude is at most 1. So, I mean, it's this whole thing is like at most like the magnitude of this. So like if w is magnitude less than 1, it's like even better because it would come over to this side. Yep.
There's a white j and a yellow j. They're different.
No, white j and yellow j are the same. Where are you looking here?
Okay, cool.
Yeah.
Alright.
Yeah.
So just to clarify, the expected yj, is it the empirical estimate?
No, it's the true estimate. Yeah, I kind of slightly glossed over that in the sense that, let me go back a little bit. Here I mean the true mean trace. And the point is, yeah, I glossed over this a little bit.
Conditioned on the true string being something?
Yeah, so I'm imagining now for all time that there's two fixed unknown distinct strings, x and x prime. And I'm considering the true mean trace under x, which is this. Well, that's the jth coordinate of the true mean trace, and the true mean trace under y. And I'm going to argue that these are at least this far apart. And then that's the reason for the sample complexity. If you estimate this, I mean by just the most basic sampling fact, if you estimate all of these mu i's using this many samples, your error will be like, you know, you can make it less than this. And therefore you can tell the difference between these two cases.
So the mu i's are the empirical estimate.
I guess so, yeah, in this notation, yeah. But I'm not going to actually talk about the empirical estimates anymore. I'm just going to show that the true mean traces are far apart. And therefore, if you estimate the true mean traces well enough, you can tell the difference. And like, how well do you need to estimate them? I mean, better than this amount by which they differ. And you know, the number of samples you need to get this accuracy is like 1 over this amount squared. And the square is negligible. I mean, I'm hiding constants here. Mm-hmm.
The previous result that had a half instead of a third, are they doing this, all this same thing, and just they have a simpler theorem here with a half, or?
No, they were not doing this. No, they were just doing it a different way. Although I guess you could get that half result if you did it like our way, but stuck to the real numbers, using this other known fact about Littlewood polynomials. Yeah.
Okay, so I'm going back to the empirical estimate part because of a certain point. So here what you would be showing is that if this is true, then for a given pair of strings x and x prime, you can distinguish with the order into the third samples.
Yeah.
But now you need to show that if x was the true string, then for every other x prime this is true.
Yeah.
Like, how would you go from there? A union bound might be pretty bad.
I think it should be okay, right? Because you only have to go worry about like 2 to the n minus 1 other strings. So you need like your probability of failing to distinguish to be smaller than 2 to the minus n. But like your sampling has like exponentially small failure probability. So maybe like add a factor of n to like the number of traces you use. You get like exponentially small probability of failing to distinguish. So I think that will do it. Yeah. The actual efficient algorithm does something slightly different. Like, I mean, it kind of tries to recover, well, let me not get into it. It tries to recover the unknown strings like bit by bit from left to right, and it uses some linear program to figure out the best, most likely next bit. But it also just relies on these estimates. Okay, so we're going to try to show that these are vectors, expected value of yj and expected value of y prime j. We're going to show that they have some coordinate where they differ by like at least a little bit in this kind of weird way. Actually, it looks weird, but it's actually, you know, this is actually true if and only if this is true. I think if you put magnitude of w equals 1. So like even though it looks like a weird move, it's actually not losing anything. It just looks weird. Okay. All right, so this is the one last thing that I'm going to skip. This is an expression that kind of looks like this expression, but again, I guess ignore for a second where we were and just stare at this. If I asked you just like, given an unknown string x, what is expected value of yj? Well, you could write it down, right? I mean, it's like, you know, the contribution to like yj, the jth trace bits, comes from all the bits of x that are at positions j or higher. And like for each position that's like higher than j, there's like some probability that like when you delete every bit with some x, you know, probability half, that like x lands on the jth spot. And that gives some contribution to the expected value of yj. Uh-huh.
So it'd be like xk plus j or something, or xj plus k? I mean like x1 and well, that's the total sum.
I think this is exactly right, but this is like exactly the thing that...
Sorry, I forgot you were summing over all j.
Yeah. 2 minutes before the talk, this is like the one equality. I was like, I got to remember why this is true. So you could write down this, okay, you could just write down this expression with like whatever binomial coefficients. Basically here though, we're taking some kind of like generating function of this expression. Like these are like n different expectations, which you could write down as a function of x and like some binomial coefficients. And like some like, you know, nice magic would happen and it would turn out to be this. Or if you're good at generating functions, which I'm not, but like sometimes I can like remember exactly how they work. Maybe you can just see this. Like somehow, right, like in generating functions, like this thing kind of, yeah, if you look at the contribution like of xk, like x, let's say the kth bit of x to this quantity, like sometimes if like no bits prior to k are deleted, you contribute xk to this quantity. Oh no, wait, so you should ask like, where does this guy contribute to over here? If no bits prior to him are deleted, he contributes to the jth term over here. You know, if like 1 bit prior to him is deleted, he contributes to the k minus first term. 2 bits, he contributes to the wj minus 2. And like that somehow like comes out of this in generating functions. Like, you know, each choice here is like a 50% chance of collecting up a power of w and 50% chance of not. Okay, obviously I'm just showing how bad I am at like generating functions, but if you don't like, I mean, some people who are like good at this are just like, this is obvious. But like if you're not like that, then you can just literally write this out and it'll turn to this. Somebody who's like really good at it, can they just say it? I don't know. Okay. Anyway. Okay, good. So, good. Okay, so I'm going to plug, you know, I have this expression appearing twice here, once with y and once with y prime. So I'll just like plug this in up here. So I'll plug this in up here. So it's equivalent to this. Yeah, it's equivalent to that. And now, like, it looks a miracle has occurred because, take a look, like, w is some complex number of magnitude at most 1. So 0.5 plus 0.5 w, if we call it z, it's like an arbitrary point in the 0.5 radius disk centered at 0.5. And these quantities here, a half of xj minus a half of xj prime, are all minus 1, 0, or 1. And the fact that x and x prime are distinct corresponds to the fact that like not all of these are 0. So this is exactly the problem we were studying. This, if you call this z, then this whole expression is a non-zero Littlewood polynomial of degree less than n in z. And the whole theorem that we spent the middle third of the talk talking about is to say that there exists some z in this disk where this value is in magnitude at least exponential in minus n to the 1/3. So of course we came at it the other way, right? I mean, somehow we had this, and then it boiled down to figuring out the best right-hand side we could put here for the value of a Littlewood polynomial on a certain disk. And that's it. So we were happy. And yeah, just one open question is, you know, find a better algorithm. I mean, the algorithm we use is very dumb. Like, it doesn't even, you could look at like, it doesn't even look at like any pairs of bits. Like, you could look at what is the probability that the first bit of the trace is 1 and the second bit of the trace is 1. Like, we don't even do that. Nor do we ever try to like align strings or anything. I mean, it's the dumbest possible algorithm. Okay, thank you.
Are there any questions?
Yes?
So you mentioned that this model is similar to like deletion channels in coding theory. Does your algorithm say anything in that situation? Like, say I want to send a message over some channel, and like, do your techniques?
Not exactly. The way it's not really similar to coding theory because like we're not encoding anything. Like our string is like the worst case. Like there's no encoding to like try to guard against the deletions. There's one like bare unencoded string that is getting deleted. So one place I saw this, I mean, come up like last year, this guy Miklos Roch gave a talk about here in the math department about storing information like in DNA, and you know, they want to like, you know, take some like, you know, 1 gig file and somehow store it in like some tiny bit of DNA and then like recover it later. And yeah, but I guess they do it without error correction. So they yeah, they put it in there with A's, G's, C's, and T's, and then like, you know, when you do your shotgun sequencing or whatever of DNA, like you get like these deletions and insertions and substitutions. You have like some difficulties. So you know, it's a pretty theoretical model of that, but like he cared about exactly this question. One major difference there though is in that problem, you can kind of assume that the unknown string you're trying to recover is randomly chosen, because you can like XOR your 1 gig data file with like a pseudo-random string. And people had studied that trace reconstruction problem before, and it's much different. So like here we talked about trace reconstruction in the worst case, like your worst enemy like wrote down an n-bit string and you get traces from it. If instead like the string that you're getting traces from is uniformly randomly chosen and you just have to succeed with high probability over the choice of the unknown x, it's much, much, much easier. In fact, like Yuval Perez and some co-authors subsequently showed there's like an algorithm for doing that with a number of traces that's sublinear. Like you don't even need n traces. So the worst case and the average case problem version of this problem are much, much different. Yep.
A worst case problem is that the n-bit string comes from a good code.
Well, a code that you yourself designed?
Sure.
Yeah.
High distance or whatever it's maxed out.
I mean, then I guess it's exactly like the problem of like designing and decoding codes for the deletion channel, which is studied a lot. I'm no expert, but you can ask Venkat if he were here, or like Boris Book, or some other people here at CMU have studied this problem. It's been studied a lot. And there, I mean, I guess you can again do a lot better. I mean, there actually you even imagine you get like one trace, and you want to like figure out what the original word was. That's possible.
I guess in some sense this is kind of like saying, what if I take the repetition code where I just like take the message I want to send and just repeat it a whole bunch of times, and you're saying I need like, I can do it.
Yeah,
like,
that's right.
The end of the 1/3 repetition.
Yeah, that's right.
You need some sort of like block icing in the middle of it.
Yeah, that's right.
So do you know what the hard examples look like?
No, I don't, although you can extract it from the proof. So it's a good point. Like what, and we have the lower bound here, so implicitly it shows, we didn't work out what the strings look like, but like it shows that there exists some pair of strings, x and x prime, which you could, I guess, somehow work out. They come out of this like complex polynomials that we construct to show that our upper bound about complex polynomials is tight, which have super close like expected traces. And they're going to look weird. It's not like, like, oh, it's like the all zero string and then like the all zero string with a 1 somewhere. Like those mean traces are like very different. And like the previous lower bounds did it by explicit constructions of like strings that looked had close mean traces based on like this two-way words or like this, I don't know, these words that you get by like some recursive construction of like making words with like no repeating patterns or something. You can ask Wes about that. I don't know what they really are. And they got this like n to the log n lower bound. And so I guess like you can extract from our lower bound for the complex polynomials problem some explicit pair of, some explicit Littlewood polynomial that has like a small value on this, only small values on this disk. And then like the coefficients of it would be like the difference vector between like the two tricky x and x primes. But I guess we didn't exactly do that per se. But yeah, that's why like the average case problem is much, much easier. Like the thing that makes it hard is like there's these like superly carefully chosen, like extremely carefully chosen pairs of strings that like look the same under the mean traces. Also, it occurs to me that it won't be explicit because the construction of these like Littlewood polynomials that are like small in the disk has like a randomized component. So I guess you won't get an explicit pair of x and x prime. Yeah.
So I mean, your algorithm, it's based on how far these mu's are.
Yeah.
Given these two x primes, x and x primes. So if I told you these mu's are reasonably far, does the reconstruction algorithm will it need much fewer?
Oh, for our efficient algorithm? You might need something like that the mu's are large, maybe like for all prefixes of the string or something. Because the algorithm, which I don't fully remember, kind of like figures out the string, unknown string x, like 1 bit by 1 bit. So like figures out the first bit, and then like it studies the mean traces, and solves an LP to figure out the second bit. So you might need something like, oh, all the mu's as you go along are far apart. But yeah, I guess, in other words, you could just like try it. And perhaps it would do well if the strings are not these like absolute worst pairs of strings.
So is it possible that these are instance optimal?
Oh, I don't know anything about that. Yeah, that's a good question though. Yeah, because this has this property that I didn't like notice before, which is that like in some circumstances, like you may be able to look at your traces and like be very confident in your answer, even perfectly confident in your answer.
But not over worst case inputs, I guess. Because like if the initial
Oh, I guess,
input is
yeah.
all ones, this is what I realized later. If the initial input is all ones, I can never conclude it's definitely all ones, right?
Yeah, I guess.
I always see ones.
Yeah, I guess until you
and I'm
see.
just like,
Yeah, that's right.
maybe it's all
Yeah.
ones. Yeah.
Let me tell you an embarrassing secret too.
This is recorded, by the way.
I know. Well, it's not the taste. This algorithm only works when you promise that every bit is deleted with probably exactly half. If I'm like, hey, guess what? I improved my thing, and now I tell you that every bit is deleted with probably at most a half, yeah, I don't know what to do. That's kind of bad, right? Yeah, so like Yuval Perez worked on that question too, and I think he has like an incomplete solution to it, but
Like an adversary chooses a probability up to a half for each bit.
yeah, that's right. In fact, even if you just know a sequence like delta 1 through delta n, where each delta is at most a half,
You even know the deletion probabilities and still.
I think I still don't know how to do it in that case. Yeah. So you could also like, maybe you'll try to estimate the deletion probabilities, but like that's also hard.
Probably in the DNA example, the deletion probability may depend on the character or something, right?
Yeah, yeah, yeah. It's a hard problem. Yeah, hard problem in the worst case. Yeah, so actually, yeah, I mean, if you're interested in like either the average case or this case where the deletion parameters are unknown, you should check out like Yuval Perez's subsequent papers, where he has some partial results. Okay, thanks a lot.